Let's go. Let's go.
Hi everyone, it's Sophia and welcome to Biology Essentials number 300. This video will be focusing on the two main growth rates, exponential growth and logistic growth, and how to solve math problems for the two models. So first, exponential growth is rapid growth, meaning there are no constraints or limiting factors on the population. Typically, this is when a species is introduced to a new environment or is rebounding from a natural disaster. On a graph, exponential growth looks like a J curve or also a hockey stick curve. For example, a few fruit flies on a large culture jar containing an abundant food source may reproduce rapidly. One female fruit fly may lay more than 50 eggs for each female that began the population. 50 flies are expected 2 weeks later. Each female in the second generation produces 50 more flies after 2 more weeks, and so on. In other words, the population is experiencing exponential growth. So an important idea of exponential growth is how we can use math to calculate the exponential growth model. To calculate the change in birth, the formula is the number of births minus the number of deaths. The formula for the exponential model is n times 1 plus r to the t power. In the formula, n is the number of individuals in the population, t is the time, and r is the growth rate of per capita of the population. To calculate r, the growth rate, the formula is births minus deaths and divided by the number of individuals. So here is one math example of how to use the formulas. One of the most common examples of exponential growth deals with bacteria. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. For example, if we start with only one bacteria, which can double every hour, by the end of one day, we will have over 16 million bacteria. Using the exponential growth formula, we can plug in 1 for n as the initial population and 1 for the rate, because if an amount doubles, the rate of increase is 100%. Therefore, we are left with t equals 1. So the formula is now 1 plus 1 to the t, or 2 to the t. Replacing the t with any hour of the day, we can see how much the bacteria has multiplied. After 2 hours, it would be 4. After 12 hours, it would be 4,096. And after 24 hours, it would be 16,777,216. As can be seen on the graph, the population of bacteria is rapidly increasing, creating a J-shaped curve. In reality, exponential growth does not continue indefinitely. There would eventually come a time when the population can no longer be sustained. Exponential growth refers to only the early stages of the process and to the manner and speed of the growth. The second growth model is logistic growth, and unlike exponential, there are environmental constraints on the population so that the population is not always constantly growing. This usually occurs after the population explodes, and the population is limited after carrying capacity is reached. Carrying capacity is the maximum population size that the environment can support without degradation of the habitat. It varies with the change in resources in the environment and with the different prey-predator interactions. On a graph, logistic growth looks like an S curve, and the line across the graph is the carrying capacity. A live example of logistic growth can be seen in a population of deer. Imagine a small population of deer in the forest. They consume the various shrubbery and low leaves of trees. At first, since the population of deer is little, there is no problem with finding enough vegetation to sustain them. However, as the population continues to continue to increase, the vegetation becomes more difficult to find. This creates density dependence, which is one of the population's intraspecific forces. Other intraspecific forces include competition for mates, territory, or sunlight, as well as diseases or parasites. As a result, the deer population grows until it runs out of resources, reaching its carrying capacity. At this point, the population levels off and decreases only slightly from there on out. Just like with exponential growth, there is a formula to calculate the logistic growth model, and this formula is dN over dt is equal to Rn times k minus n over n. K in this formula is the carrying capacity. A key difference between using the exponential growth and the logistic growth model is that in the logistic growth model there is a carrying capacity. So here is one math example of how to calculate the logistic growth in a population size of 2 individuals with a carrying capacity of 100 and a growth rate of 0.5. In this problem, n equals 2, k equals 100, and r equals 0.5. Once you plug in all the numbers into the equation, the population growth can be calculated to be 0.98. So in conclusion, the two population growth models is exponential and logistic, and exponential growth is more unrealistic because there are no limits and there's unlimited resources, whereas in logistic growth there is a maximum limit and a carrying capacity. Cue the music. Today we're talking about pop growth rates, and the first one is exponential. Population keeps growing at a really fast rate. I have no limits, got a lot of resources, gonna reproduce, gonna keep them coming. That's right, there are no constraints because this is exponential. Few times I multiplied real fast, but I'm not just gonna end like that because I'm a J-shaped curve. I'm just gonna keep growing. A few times I multiplied real fast, but I'm not just gonna end like that. I'm a J-shaped curve. I'm just gonna keep growing. Ooh, this my graph. This my graph. 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 So here's what's next. According to the text, no population grows like that. Both of us want to be the winner, but there can only be one. So I'm gonna fight, gonna give it my all, gonna take your food, gonna dominate you. That's right, I'm logistic growth, you hit the carrying capacity. A few times I try to grow real fast, but the real world doesn't work like that because we have limited resources and we have to compete to live. A few times I try to grow real fast, but the real world doesn't work like that because we have limited resources and you have to compete to live. Ooh, this my graph. This my